Welcome to the Calculus lecture series. My name is Young-Soo. Today we will go over implicit differentiation. Implicit differentiation is a powerful concept. Potentially, the technique you will learn in this lesson can save your time tremendously. Let's say you are given a function y is equal to 2x squared plus 5, and you want to compute its derivative, dy dx. A usual way is to take the derivative directly. That is, you can take a derivative of the right-hand side with respect to x and get 4x. Very easy, right? This way is taking a particular view though, which I call it explicit view, where you explicitly set x as an input variable and y as an output variable. By the way, this is not the only way of getting the derivative. The other way takes implicit view, where you treat both x and y variables the same way. Therefore, there is no input or output variables, so we cannot consider an instantaneous change of output over the change of input, which is the definition of derivative. Instead, we focus on the instantaneous change of each term. For example, let's look at the instantaneous change of y, which is the left-hand side term. We denote the instantaneous change of y as dy. Next, let's move on to the right-hand side terms. The first term is 2x squared. In order to get an instantaneous change of this term, we will use the chain rule. First, take the derivative of dx squared with respect to x, which is 4x. This represents the instantaneous change of 2x squared of the instantaneous change of x. By the way, we are only looking for the instantaneous change of 2x squared, which is on the top. Somehow we need to get rid of the bottom. We can do this by multiplying it by the instantaneous change of x, that is dx. Now the instantaneous change in x cancels out, which finally gives us the instantaneous change of 2x squared only. By the way, the second term of the right-hand side is 5, whose instantaneous change is 0 because it simply does not change. Finally, we can equate instantaneous change of the left-hand side with the instantaneous change of the right-hand side. Now you can get two different types of derivatives. The first one is dy dx, which you can get by dividing both sides by dx. So it becomes 4x. Note that it is the same as the derivative you got with the explicit approach. The other one is dx dy, which you can get by dividing both sides by 4x dy, which becomes 1 over 4x. The first derivative, dy dx, treats y as output and x as input, while dx dy treats x as output and y as input. Now you might wonder what is the usage of taking this implicit view of differentiation. It seems very complicated and take a very long detour, while the explicit approach gives you the answer right away. You are exactly right. For this particular problem, the explicit approach is much easier than the implicit approach. However, there is a great advantage of taking the implicit approach for a certain type of problem. One such problem is given here. Let's say, for example, you are given an equation for a circle with a radius of square root of 5. Then you are asked to find the equation for the tangent line at a point 1, 2. If you take an explicit approach, then you gotta first transform this equation of the circle as an explicit function of x. That is, y is equal to square root of 5 minus x squared. Strictly speaking, you have to consider one more explicit function of x. That is, y is equal to minus square root of 5 minus x squared. However, this particular explicit function does not pass the point 1, 2, right? So we can ignore this second explicit function. Now, if you take an explicit derivative for the first explicit equation with respect to x by the chain rule, After some arithmetics, you will get dy dx equals minus x over square root of 5 minus x squared. Now let's obtain the derivative in implicit way. Here you do not have to transform the equation for the circle to an explicit form. Instead, you treat each variable in a same way and try to compute the instantaneous change of each term. If you do that term by term, then you will get 2x dx for the first term and 2y dy for the second term. And the right-hand side will be 0 because 5 does not change. Now, if you divide both sides by dx, you get 2x plus 2y dy dx equals 0. From here, it is easy to get dy dx. After some manipulation, you will get dy dx equals minus x over y. Now you can plug the point 1, 2 to both derivatives to obtain actual derivative value at that point. You will notice that both explicit and implicit approaches gives minus 1 over 2, which represents a slope of the tangent line at the point 1, 2. Therefore, the equation of the tangent line becomes y minus 2 equals minus 1 over 2 x minus 1, which can be simplified further to y equals minus 1 over 2 x plus 5 over 2. What do you think? Which one do you think is easier? For this particular example, you might still think that both explicit and implicit approaches are about the same. However, the problem can be complicated enough that the implicit approach will give you much simpler way of getting a derivative. For example, try to solve the following problem where the implicit equation is given by x squared y plus 6xy squared equals 5x squared plus 3y minus 3. And you are asked to find dy dx. If you try to take an explicit approach, you will easily find yourself with very complicated terms. On the other hand, if you take the implicit approach, then you can start to take a derivative of each term, considering both x and y in the same way. For example, the derivative of each term will be 2x dxy plus x squared dy plus 6 dxy squared plus 12xy dy equals 10x dx plus 3 dy. Now dividing both sides by dx gives 2xy plus x squared dy dx plus 6y squared plus 12xy dy dx equals 10x plus 3 dy dx. Now if you collect all the dy dx terms on the left-hand side and all other terms on the right-hand side, you will get x squared dy dx plus 12xy dy dx minus 3 dy dx equals 10x minus 2xy minus 6y squared. Now, if you factor out dy dx term on the left-hand side, you get x squared plus 12xy minus 3 dy dx equals 10x minus 2xy minus 6y squared. Finally, dividing both sides by x squared plus 12xy minus 3, you will get dy dx equals 10x minus 2xy minus 6y squared over x squared plus 12xy minus 3. All right. I hope this lecture was helpful to understand why you want to take an implicit approach when you take a derivative. If you think this was helpful, please push the like button and share this video with your friends so that your friends can get benefits from this video. Also, I will post other calculus lectures in near future, so please stay tuned and do not forget to subscribe my YouTube channel. Also, if you have any calculus materials that you want me to cover, please leave it in the comment below. All right, see you next time.